So this is 3.9a continued, and I guess I'm example 3 now. Yeah, that's right. And I've got f of x equals 2 to the x, and we're going to find f prime. Okay, so at this point, we are getting pretty good at taking derivatives of a letter to a number. So for example, if it's x to the 5th, we're good at that. We've got a shortcut for that, and we're using it a lot. That's called the power rule, right? This is different. This is a number to a letter. So power rule does not apply. It would be tempting to bring the x out front and subtract 1 from it, right? So if I asked you to take the derivative of this and you didn't have any warning, you probably would write this. But that doesn't work. Okay, so this shortcut that I just used only works on letter to number. It doesn't work on number to letter. So we need a new shortcut for situations that are, these are called exponentials, when you have a letter that's an exponent. So we need a new shortcut for this. So when we don't know what the shortcut is, how do we take the derivative? Yeah. You have to go back to the nasty limit h approaches 0 or whatever method, right? The definition of the derivative. Now, by the end of today, we're going to have the shortcut for this. But temporarily, I'm going to go back to the way you have to do it when you don't know the shortcut. Okay? So we're going to take the limit as h goes to 0 of f of x plus h minus f of x all over h. Need to erase this because it's not right. It makes me nervous that it's up here. Don't even want people looking at it because it's just not right at all. Okay, so here's the way you take the derivative. And you could do the x approaches a method. It's the same exact thing. Just h approaches 0 turns out a little bit better for this function. And so that's what we're going to use for this one. Okay, so we got to plug in what f of x is. So that is 2 to the x. And I'm just recopying the h and the division sign. And then this part means plug x plus h into f. So that's going to be 2 to the x plus h. If I plug 7 into f, it would be 2 to the 7th. If I plug 58 into f, it's 2 to the 58th. So if I plug x plus h into f, it's 2 to the x plus h. So this is the regular formula for a derivative, and now I'm just applying it to that function that I'm trying to take the derivative of. Everybody okay so far? Okay, now this piece here, 2 to the x plus h, I'm going to split that up into 2 to the x times 2 to the h. Because when you have a base that's the same, you can add the exponents, right? So for example, if you had x cubed times x squared, that would be x to the 3 plus 2, right? It would be x to the 5th. So now I'm going backwards. It's not very often that we go from there to there. Usually we go from here to there. But I'm going backwards with the 2 to the x plus h. I'm writing it as 2 to the x times 2 to the h. Everybody okay with that? All right, and I'm going to just recopy everything else. Minus 2 to the x all over h. Take the limit as h goes to 0. Okay, then these both have a 2 to the x, so I can factor that out. So it's 2 to the x times 2 to the h minus 1 all over h. That's the limit as h goes to 0. So I just factored out the 2 to the x. If I multiplied it back out, it would be 2 to the x times 2 to the h. That would be that. 2 to the x times 1 is 2 to the x. All right, now this is multiplication right there. And this piece of it doesn't have anything to do with h. It's just 2 to the x. So as far as h is concerned, this is a constant. And the limit, when you have the limit of a constant times a function, you can bring the constant out front. Or you can take the limit of the constant and just get the constant. Okay, so I'm really distributing the limit. I guess maybe I better write that step down. I'm taking the limit of the 2 to the x times the limit of the 2 to the h minus 1 over h. So limit laws distribute to multiplication. That's what I'm doing there. The limit of that times the limit of that. And then I was kind of talking ahead and talking about the fact that the limit of this constant is just the 2 to the x. Okay, so at this point we've boiled it down to this limit here. And we're going to make a table to figure out what that limit is. By the end of the day, we're going to know what that limit is exactly. But for now, we're going to get a decimal for it. Okay, so just plug in like 0.1, 0.01, negative 0.1, negative 0.01. If you've got your calculator, maybe plug one of these in, and I'll go get mine so I can figure out what those are. I'm getting 0.7177. Everybody at least able to get one of those numbers? Okay, so it's getting close to maybe, your guess is as good as mine at this point based on these numbers. I'm just going to say it's getting close to 0.69. Okay, so I'm rounding, and again, we'll have the exact answer by the end of today, but for now we're just going to call this 0.69. Okay, so we took our derivative, and we got the derivative to be about 2 to the x times 0.69. Okay, so now we're going to do this again with a different function. f of x equals 3 to the x. So remember, our goal is to find a shortcut for how to take derivatives of things like that. How to take derivative of a number to a letter, because we don't yet know how to do that. So we tried 2 to the x and we've got something, but we don't have a pattern yet. So now we're going to try 3 to the x and see if we can establish a pattern. Okay, so we're going to do the same thing. Take the derivative of this. The derivative is the limit as h goes to 0 of f of x plus h, so 3 to the x plus h, minus f of x, so 3 to the x, all over h. So same idea as before, it's just the function has changed. Instead of 2 to the x, it's 3 to the x. So I'll still be able to split this up into 3 to the x times 3 to the h. And I'll still be able to factor out the 3 to the x. And I'll still be able to split up the limits into the multiplications, right? Limit of the first thing times limit of that mess. The limit of 3 to the x is just 3 to the x, because that's a constant as far as h is concerned. And then I'm boiling it down to this limit of 3 to the h minus 1 all over h. So I went through that. I explained it a lot less that time because I explained more there, but if I lost you there and there, be a good time to ask a question if you're not sure about some of these steps that I went through quickly. Okay, so I boiled it down to this limit, right? So I'm going to make a table for this limit again. Let's see how that goes. Wondering if I have that. Yeah, for point 1, I got another year, 1.162. For point 01, I got 1.1047. I don't have the negatives written down, so I'll punch those in real quick. So it looks like it's getting so close to something like 1.09 or maybe 1.10. So I've got an approximate derivative again, f prime of x is about 3 to the x times 1.09, I guess. Okay, so we're kind of on our way towards establishing a pattern. If the original function is 2 to the x, then the derivative is 2 to the x times a number. And if the original function is 3 to the x, then the derivative is 3 to the x times a number. And that's the way the pattern goes. It's always the original function times a number. Okay, so if f of x equals a number to the x power, so now I'm generalizing. Instead of 2 to the x or 3 to the x, I'm saying any number to the x, a to the x. Then what's going to happen is the derivative is going to be just a number times a to the x. So I switched the order. the way we wrote it there, it was 2 to the x times the number, but that's the same thing as the number times 2 to the x. Okay, and I'm going to tell you what this number is in just a second. But before I get there, notice that this number is bigger than 1. And this number is smaller than 1. And what would happen if this number was 1? Then the original function would have the same exact function as its derivative. Let me say that again. If this number here was 1, then the f of x function, the heights, would be the same exact function as the slopes. So it'd be kind of cool if we knew what happened when that happened. Okay, so for 2, it's less than 1, right? The number. And for 3, it's bigger than 1. So it goes to show that that's going to happen for an a that's somewhere in between 2 and 3, right? Any guesses on what it could be? Some number in between 2 and 3. It's e, yeah. E is 2.71828. Okay, so off to the side here, this is an interesting fact. If f of x is e to the x, then the derivative is also e to the x. That is kind of strange. Because usually the original function and the derivative are different functions, right? But this is an example where the original function and the derivative function turn out to be the same function. So that's why e is such a big deal in calculus. And then remember when I said yesterday that I like to take the natural log of both sides? Because you can pick any log. And that's because e is such a famous calculus number that in calculus we tend to use e more. And it's because of this, because if f of x is e to the x, the derivative is also e to the x. Okay, so, but that just works when the number is e. But we need to know what this is when the number is 2, and when the number is 3, and when the number is 58. Okay, so it turns out that this number is the natural log of a. So real quick, just punch in natural log of 2. And is it close to 0.69? Yeah, so the exact, remember this was just a rounded answer. I didn't know what the limit was exactly previously, but now I know it's actually the natural log of 2. And then punch in natural log of 3. And if I did everything right, it should be close to 1.09. Okay, so now we know the shortcut for how to take the derivative of a number to a letter. What you do is you take the natural log of the number, and then you just times by the number to the letter. Does that work for this one? What's the natural log of e? It's 1. So you don't even have to memorize this. You could just memorize this, and it would work for e as well, because the natural log of e is 1, and so you're going to get e to the x. The reason the natural log of e is 1 is this says e to what power is e, right? And it's e to the first power that's e. So that's why the natural log of e is 1. Logarithm says e to what power, or 10 to what power, or whatever the base is. We'll talk more about that as we get into it more. But okay, so we have a brand new shortcut. Here it is. It's how to take the derivative of an exponential function. And then a side note is that this is an interesting function where the original function and the derivative are the same. Okay, so that was all discovering the shortcut and understanding where it comes from. And now we're going to work with it. All right, so we're going to have f of x equals e to the negative 5x. And we're going to find f prime. Okay, so this is not just e to the x. If it was just e to the x, what would the derivative be? E to the x, right? And it's kind of like that, because it's e to something. But this is a composition. And it's hard for people to see that at first. Okay, so this is the function e to the x with negative 5x plugged into it. So if you have the function e to the x and you put 2 into it, then it's e squared. Or if you put 7 into it, it's e to the 7th. So if you put negative 5x into it, it's e to the negative 5x. Okay, so this is a kind of a critical moment here. Does everybody understand that that's a composition? Outside function is e to the x, and inside function is negative 5x. Negative 5x is getting plugged into there. Okay, so now, since everybody's saying they understand that that's a composition, how do you take the derivative of a composition? It's called chain rule, right? So you take the derivative of the outside function. Here's the outside function. What's the derivative of e to the x? Just e to the x. So you take the derivative of the outside, and then you plug the regular inside into it. So that's going to be e to the negative 5x. So there's the first 2 steps of the chain rule, right? It happens naturally even if you don't know that chain rule is supposed to happen, right? If you see e to the negative 5x, you would just assume that, right? And you wouldn't even think chain rule. So the first 2 steps of the chain rule happen naturally. It's the 3rd step that people forget about. They don't recognize this as a chain rule, and so then they forget to multiply by the derivative of the inside. The inside function is negative 5x. The derivative of that is negative 5, so I need to times this by negative 5. I could put times negative 5 at the end, or I could put times negative 5 at the beginning. It doesn't matter. So now I've got my f prime. Is everybody okay with this? All right, let's try y equals the cosine of 8 to the x. So what do you think about this one? What kind of a function is it? It's a composition, good. What's the outside function? Cosine, right? What's the inside function? 8 to the x is getting plugged into cosine. People are more comfortable with this being a composition than they are with this, because this looks a little different than what we've seen before. But we've seen stuff like this before, cosine with a bunch of junk inside of it, right? Okay, so you take the derivative of the outside, then you plug the regular inside into it, and then you multiply by the derivative of the inside. So we have to take the derivative of 8 to the x. That's the new shortcut, right? So what is the derivative of 8 to the x? Yeah, give it a shot, Brandon. You're looking in the right spot.
Is it the natural log of 8 times
Perfect. It's the natural log of 8 times 8 to the x. Everybody okay with that? Okay, and then there's this whole issue of whether it's the sine of all of this or whether it's this times that. So we generally put that at the beginning. So I would write it like this. Natural log of 8 times 8 to the x. I'd even put the negative probably here, because it's like -1 times those things times the sine of 8 to the x. This looks terrible. Everybody in the room wants it to simplify to something else, including me. It doesn't. We're stuck with this. You could type in natural log of 8 in your calculator, right? The problem is that decimal goes on forever. So anything you write down is going to be a rounded version of it. So better to leave it natural log of 8. All right, let's do this one. Let's say we have y equals 7 to the square root of x. So what kind of a function is this? Composition, right? What's the outside function? 7 to the x. And then square root of x is plugged into it, right? Okay, so you take the derivative of the outside. And then there's a blank up here, right? That's the derivative of the outside. The outside function is 7 to the x, so the derivative is natural log 7 times 7 to the x. Then you plug the regular inside into it. So now we're done with the first 2 steps of the chain rule. And then we need to multiply by the derivative of the inside. So we have to take the derivative of square root x. So that's 1/2 x to the -1/2. Is everybody okay with that? Okay, so I'm not saying that product rule won't happen with the new shortcut. I'm not saying quotient rule won't happen with the new shortcut. But chain rule is the hardest one to deal with the new shortcut. So that's why these examples are dealing with chain rule, right? But there could be a product rule. You could have 7 to the x times something else and then have to do product rule with that. Or there could be 7 to the x divided by something else, and then you'd have to do quotient rule with that. But those rules are a bit easier to deal with, so that's why I'm not doing examples of that with the new shortcut. Is everybody doing okay? Are you sure? Okay, I think I've said everything I need to, but I'm going to just double check, because sometimes I leave stuff out. Yeah, that's okay. I do want to